I wish you guys well. Hope you guys are enjoying the homework. Today we continue with our theme here, polar coordinates. Last time we introduced the contrast between the old Descartes system, the new ideas, the Pinocchio system, the polar coordinates, where you just turn and face whichever way you want to go and then go either forward or backwards depending on r is positive. We also talked about the famous bridge, how to go from here to there and going backwards, and the idea that going backwards could happen in many different ways, infinite many. What we want to do today is expand on that. We want to actually do some graphs. Let me just remind you how this happened before. For Cartesian coordinates, it's a common problem to give you an equation. They ask what are the solutions to that equation, and to actually plot such solutions on a plane. And this is a famous one. This is if you've never done it before, what you would do is you would make a little chart here with x's and y's, and you take various values for x. Let's say, for example, x equals -2, -1, 0, 1, 2. For each one, you would put it into the equation and find out the corresponding value for y. In this case, it'd be 4, 1, 0, 1, 4, and then you would plot them 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. And once you have enough points, you can connect them smoothly. You've got success. That's more or less how it happened in previous courses. What we want to do today is do exactly the same thing, but for polar coordinates. So, what would a polar coordinate equation look like? Well, instead of having y's and x's, it would have r's and thetas. So what we want to do is become good at graphing. Now there are different levels of graphing, different methods for graphing. Even here there are different methods. The first thing you can always try is plot points. And that's going to be our first attempt, by plotting points. Plot points, which basically means make a chart like this with the various points, enough to where you can just connect them smoothly. This will be exactly the same method that we can try on polar coordinates as well. And then after we do that, we want to take it up a notch or two, where we perhaps use more sophisticated ideas rather than just plotting points. Such as we did here. We had the shifting principles, the stretching principle, a lot of different ideas that were a little bit more sophisticated than just plotting points. Nevertheless, this is a good place to start, plot points. So I ran some points through a spreadsheet. You could do this on a spreadsheet, or you could do it on a calculator, punch numbers, and here's an example. Suppose I give you that r is equal to 3 plus 4 sine theta. As promised, these equations will have r's and thetas. And you can make a little chart with all the different kind of angles that you want. So I tried multiples of 10. I tried 0 degrees, 10 degrees, 20 degrees, 30, 40, 50, all the way to 360. Actually, all the way to 370. Because after that, they start repeating themselves, because sine is not going to care whether it's 10 degrees or 370. So there's no point in going on beyond that, at least for this particular equation. For each corresponding one, for 10 degrees, I plugged it in here, sine of 10 degrees. Then I multiply it by 4, then I add 3, and I get the corresponding r value. For example, for 0 degrees, for 0 degrees, if we look in the 0 degrees direction, by the way, we have to bring our Pinocchio here. Look in the 0 degrees direction, and then you go out, how many units? 3. So the first point would be right here, 0, 3. 1, 2, 3. That marks the spot. Okay. The next one for 10 degrees is 3.69. So for 10 degrees, well, where's 10 degrees? That would be somewhere around here. This is 30 degrees, mind you. This is 30 degrees. This is 60 degrees, and so on and so forth. For 10 degrees, it's 3.69. I'll just estimate. This is 3.69 would be a little bit more than a half. For 20 degrees, it'd be 4 point something. For 30 degrees, it'd be 5. 1, 2, 3, 4, 5. For 40 degrees, I'm just going to skip a few. For 60 degrees, it's 6.4. So 1, 2, 3, 4, 5, 6, 6.4. For 70 degrees, it's 6. For 90 degrees, it's 7. It's all the way to 7. 1, 2, 3, 4, 5, 6, 7. For 120 degrees, it's 6.4. So it's coming back down to 6.4. For 150 degrees, it's 5. 1, 2, 3, 4, 5. For 80 degrees, it's 3. 1, 2, 3. So far I've gone something like this. If I connect the dots as smoothly as I can connect them, that's what it's done so far, just by plotting points. For 210 it's 1, so when I look in the 210 degree directions, it's 1. For 270 it's negative 1. Whoa, for 270, as I look in this direction, I've got to go negative 1. That would put me back here. Now I've gone this way. Let me think. For 330, it's 1. 270. For 300, it's 0.46. So when I look in the 300 degree direction, it's around here. 0.46. For 330 is 1. So 330 is 1. And for 360, I'm back at 3. And there you go. Super famous. The idea is just take your equation, plot a whole bunch of angles. For each angle, figure out the corresponding R, and then make dots and connect them. And actually, this is really famous. That's the first lesson. You can always graph something by plotting points. Okay, this is perhaps the most basic method that you can possibly have. There isn't much thinking. There's no creativity. All you got to do is do the work. Make a little table and plot the points carefully. Okay. You really should do this on your own. I've posted some good homework prompts so that you can actually plot them and get a feel for it. Okay, that's the first method for graphing polar coordinates, polar graphs. The second idea that I think is a good one to graph polar coordinates is to graph not by plotting points per se, but by recognizing famous graphs. There are a few graphs that always come up over and over again, and it's probably good for you to get to know them, recognize them. That way you don't have to go through the plotting points all the time. This is not that advanced. It's only one little tiny notch above the plotting points method, but we'll take it. Let me run through some of the famous graphs. Every time you've got R is equal to any constant, I don't care what it is, 7, plus some other constant, for example, I don't know, 10, and you multiply the second constant by a sine or a cosine, only those two, a sine or a cosine. Let's say a cosine of theta, just like this. This is a famous type of equation, and it always has the same type of graph. The graph will be one of these three. It'll either be one that, like the one we had right now, where you have kind of a little heart-shaped thing with a little bubble inside, or it will be one with no bubble inside, or it will be one where the bubble never came to be. Okay? It'll always be one of these three, but they may be shifted 90 degrees depending on whether this is sine or cosine, or they may be flipped depending on whether this is positive or negative. But they all have shape more or less like this, and depending on which is bigger, the 7 or the 10, will determine whether it has a bubble or no bubble. If they're equal, it'll have just this little cusp thing, little corner. And to know which is which, there's really nothing to memorize. Just recognize that this is a famous form. And then what you could do is just plot 4 points. That's all you got to do is plot 4 points. Let me explain how we can do that. So I'm going to take this one, and I'm going to clone this page, and we're going to get rid of this and figure out which one is it. with nothing but, whoa, common sense. Let's ungroup this so that we can delete that, and delete that, and delete that, and delete that, delete that. So here's what I propose. All you gotta do is plot, I propose that we plot 4 points, and 4 points only. And with those 4 points, we'll be in good shape. By the way, I want to clone one of these graphs so we can plot them. By the way, soon I'm gonna put some graph paper on the website where you can actually print some nice polar coordinate graph paper. That way you can do these as nice as I'm doing them here. Let's copy this and let's see which one this is. So I'll paste it here. Now we're in business. All right, so here's what we can do. I propose all you gotta do is plot 4 points, and the way you plot the 4 points is like this. You look to the north, that's 90 degrees direction when you're looking to the north. You look to the south, that's 270 degrees direction. You look to the east, that's 0 degrees, and you look to the west, 180 degrees direction. That's all you got to do. With these 4 points, you will be able to determine which one of these it is and exactly which way it's facing. I promise you. Watch this. Let's look to the east. Let's look at 0 degrees. So if you plug in 0 into here, cosine 0 gives you 1. That's 10. That's 17. So this would be 17. So you go 17 units. Let's just say each one of these counts for 3. So 1, 2, 3, 4, 5, that would be 15. 17 would be right around here. Let's go with blue. You guys want to go with blue? There's 17. Check. Let's look to the north. For 90 degrees, cosine of 90 degrees is 0, so that becomes 7. So when I look to the north, that's 7. That's why it'd be 6, 7. We said each one of these was worth 3, right? Let's look to the west. That's 180 degrees direction. This is -1. That becomes -3. Because this becomes -10. 7 and -10 becomes -3. So if I'm I'm facing the 180 degrees direction, I got to go backwards. 1, 2, 3. Backwards would put me down over here. There's only one way to get that. Which one of these would have to be where you got 17 when you look to the east, 7, and then you got to go backwards when you look to the west. It's only the one with the bubble. These ones don't go backwards. So that settles it. This one is, if you accept it's one of those 3, it has to be the one with the little bubble inside. And then just for fun, you could look south. That's 270. 270. That would be. Here's a cosine graph in case you forgot. This is 180. 270 would be 0. So this would be 7. So right here. And then of course we'll put you back there. Okay, this is called recognizing a famous one. These are all super famous. Here, let's try another one of those super famous ones. Let's try this one. R is equal to 5 minus 5 sine theta. Again, a constant, another constant, and a sine or a cosine theta. If you got it exactly like this is super famous. It's one of these, except it might be shifted or flipped, but it's one of these shapes for sure. Okay, if you don't know which one it is, it's easy. You just plot the 4 important points: 0 degrees, 90 degrees, 180 degrees, 270 degrees, and you're good to go. 0 degrees. Sine of 0 is 0, so you're looking at 5. 1, 2, 3, 4, 5. 90 degrees. Sine of 90 is 1, so this becomes a 0. Okay. 180 degrees. 180. That would be 0 degrees. Okay, so 180, sine of 180 is 0, so that kills that part. It just leaves you with a 5. That means that as I look in the 180 degrees direction, I go 5 units. 1, 2, 3, 4, 5. And then I look in the 270 degrees direction. That's looking south. And for 270, This becomes -1 times a -5. That becomes +5. That gives you a total of 10. So that's way down here. You can't see that far, but it's, believe me, it's way down here. It's 10 units apart. So then, only way that this could happen is it's this one right here. It goes through the origin or the pole, and it doesn't go backwards, and it makes it to the pole. In fact, every time that these two are equal, you'll have that little corner. So the way we draw it is like this. It has to go through here, has to go through there, has to go that way. Okay? Nothing to memorize, just plot these four and figure out which of these three fits the bill. So long as it's constant plus another constant times cosine or sine, it'll be one of these three. That's the beauty of it. So that's the second way of graphing. Recognize famous ones, and these are all super famous. In fact, there are some other ones that are super famous. Let's talk a little bit about those other ones that are super famous. Clone. Okay, so these type of equations are also very common. They're very famous. They go like this. They have a single r here. R is equal to some constant times a sine or cosine. Either way, it's famous. And then a theta or an integer multiple of theta, like 2 or 3, positive or negative multiple of theta. But it has to be a whole number. If it's a whole number like this, an integer, this is a famous form, and it has famous graphs on them. But if you've never seen it before, then it's not really that famous to you, is it now? So what's the one thing you could always try? You could always try plotting points the way we did over here. Plotting points will always work. But now I'm going to propose that we take it up a notch or two. Rather than plotting points, let's actually think about what's going on here. R is equal to the distance from the pole to the point, right? Now R could be big or small. And let's think about this carefully. How big could it be, or how small could it be? R is equal to 5 times the sine. This sine guy right here, the sine piece, the sine of anything, any real angle, the sine of any angle, real angle, will always be between 1 and -1. It'll never ever be larger than 1, and it'll never be smaller than -1. So if this is a piece, this number's got to be bigger or the -1, but smaller than +1, or equal to. And it's being multiplied by 5. That tells you that your R could never ever grow beyond 5 or less than -5. The maximum possible value of R is 5, and the minimum possible value of R is -5. You get it? We're just trying to analyze the situation so that we don't just sit there and plot points like an insect would. We have to try to think like a human and not think like an insect. So we're trying to think, alright, R can get no bigger than 5, no smaller than 5. That means 1, 2, 3, 4, 5. The whole picture has to fit into this piece right here, inside the circle of radius 5. No matter what, the picture will never be outside of that. Clear? Not only that, but suppose I could find out where it reaches its maximum. Where does it reach its maximum or minimum? What would that say? That's a crucial question. Where does it reach its maximum? Where does R reach its maximum or its minimum value? Well, it would reach it whenever. Let's do it this way. R. Let me do a little analysis here. R would be max or min. Well, let's just do max first. R would be max out whenever sine of 3 theta is equal to 1. That's the maximum possible value of R. Whenever this piece is 1, it's reaching its full potential. And when would that happen? Well, this, my friends, this is an equation, an almost easy equation of the type we solved last chapter. We could solve it. We could just make a little graph here. Here's a sine graph. It reaches 1 at 90 degrees. So 3 theta must be a multiple of 3 theta must be equal to 90 degrees, or any integer multiple of 360 added to that. So, right? You remember doing this, right? So therefore theta could be 30 degrees plus any multiple of 120 degrees. So at these points, R reaches its maximum potential. So that means that, for example, at 30 degrees, if I look in the 30 degrees direction, what's it? For 30 degrees, this would be 3 times 30 would be 90. Sine of 90 would be 1. That would be 5. 1, 2, 3, 4, 5. It reaches its maximum here. That means it can never, the graph cannot go like that, because that would be a larger R. So at this point, it must be like this. That's what it means to reach its maximum potential. That around there, the R has to be smaller or closer to the origin. Does that make sense? So for sure, that little piece has to look like that. Not only that, but it does it again if you add 120 to it. So 30 plus 120, that's 150. At 150, it does the same thing, and it reaches. This is 1, so this is 5. 1, 2, 3, 4, 5. It reaches its max there as well. And if I add 120 to that, I'm at 270, and it reaches its maximum there. This will be equal to 1. 1 times 5 is 5. 1, 2, 3, 4, 5. It reaches its maximum there. So we know for sure the graph goes like, at least it goes through those points, and has some sort of shape this way because it reaches its maximum value. Around it, the value's got to be smaller because the sign decreases. See that? Just thinking about it in a much more sophisticated way than just plotting points. If you like plotting points, go for it, but this may be nice too. I like this. Anyways, that's not the only way that you could have a tip like this. If R reaches its minimum, that just means we're walking backwards. The same thing could happen. So now I have to analyze when does it reach its minimum. Well, the minimum would happen here. I'll do the minimums in green. At 270. So if R would reach its minimum if sine of 3 theta is equal to negative 1. And that would happen if 3 theta is equal to 270 degrees plus any integer multiple of 360 degrees. So that would mean that theta is equal to 270 divided by 3. That would be 90 degrees plus any multiple of 360 degrees. So at these points, 90 degrees, well, multiples of 120, I divided everything by 3. At these points, R reaches its minimum. It can never go backwards more than that. So at 90 degrees, 1, 2, 3. At 90 degrees, this would be negative 1, so this would be negative 5. So you go 1, so at 90 degrees, here's 90 degrees, I got to go negative 5. 1, 2, 3, 4, 5. It's exactly the same one. And then I add 120 to it. That would put me here. Add 120 plus that would be 90 degrees. If I add 120, that would be 210. If I add 120, that would be 330. These are the points where you reach its minimum. So let's do the 210. So if I look in the 210 degrees direction, this part right here becomes negative 1. That becomes negative 5. So I walk backwards 5. 1, 2, 3, 4, 5. That would put me right at that point. Same for 330. If I look in the 330 degree directions, I would have to work backwards 5. And it tells me the graph has to go through those points. And that's it. We will use that. You could always plot points, but this is famous. The graph will look like this. It'll look like it rose, and these points, wherever R reaches its maximum potential or its minimum potential, those points right there are the tips of the petals, because the R can't go further than that. And that, my friends, that's super, super famous. R is equal to 5 sine theta. Super, super famous. Can you believe it? And then you could do this for all sorts of integers here. You could try, instead of the 3, try a 1 or a 5 or a 7 or a 4 or a 2, whatever. Instead of a sine, you could try a cosine. Instead of the 5, if you had a different number, that would just change the diameter of these rose petals. That's fine. You want to try something? You want to try another one? Let's try another one. Let's try this one, see if you guys are afraid. R is equal to 5 cosine 2 theta. Again, we could always plot points, but we want to elevate that just a little bit beyond that and try to think about it in a more sophisticated way. Take it up a notch or two. The critical analysis is when does R reach its maximum or its minimum value, because at those points you have to have tips of petals, because R is the distance from the origin. So if that's the maximum distance, it has to be a petal. Alright, enough talk, let's do it. So R would reach its maximum. Let me do the max. I like red, let's do red now. R would reach its maximum whenever cosine 2 theta is equal to 1. And I make a little graph here. This is my cosine graph. Whenever it reaches 1, well, that would mean that 2 theta is equal to 0 degrees plus any multiple of 360. So 360 integer multiples. So therefore theta is equal to 180 degrees multiples. So that means that at 0, 180 degrees, 360, etc., it reaches its maximum. So let's go with 0. If you look in 0, this becomes 1, so that becomes 5. So in the 0 degrees direction, you go 5. 1, 2, 3, 4, 5. There's got to be a tip of a petal right there. Plus multiples of 180. So if I add 180, I'm at 180. I got to go, this becomes 1. Cosine of 0 is 1, or 180 times 2 is 360 becomes 1 times 5 is 5. So 1, 2, 3, 4, 5. That's got to be a petal too. Tip of a petal. 360 gets me back to the other one, so it's just a repeat. I won't even do it. And those are the maximum values of R. Now let's look at the minimum values of R. R would reach its minimum. The smallest that cosine could be is -1. So the smallest that R could be would be -1 times 5. Would be -5. And that would happen whenever cosine 2 theta is equal to -1. When would that happen? Well, that would happen here. It would happen at 180. When 2 theta is equal to 180 degrees plus any integer multiple of 360 degrees. That will tell you that theta is equal to 90 degrees plus any multiple of 180 degrees. So this gives you, for example, 90 degrees to 70 degrees plus 180, etc., etc., etc. So whenever I look at 90 degrees, here I'm looking at 90 degrees, this becomes -1. I got to go backwards, -5. 1, 2, 3, 4, 5. That puts me right on this spot right here. Okay. 270. So now I look at the 270 degrees direction. I'm looking this way. This becomes -1. That becomes -5. I got to walk backwards 5. 1, 2, 3, 4, 5. There it is. That tells me there's a petal there. Something curious happens here when you look at when you analyze the maximum and the minimum values of R. Whenever the integer is even, just so happens to be this way, whenever the integer is even, they will not repeat each other, so you have twice as many petals. Here we're going to have 4. Whenever it's odd, they actually overlap each other. And you can think about why that's true. But the end result will be that, as in this case, we will get twice as many petals. If you don't believe me, you could try plotting points. Beautiful. See a rose with 4 petals. It'll always generally be the case if this is even, they won't overlap, the max and the minimum. So they have twice as many. When it's odd, they will overlap just like they did before. And you just have that many. Interesting, huh? Very nice analysis of the equation so that you can figure out where the tip of the petals are. Alright, I think I'll stop here. You should read the homework, read the notes. It's incredibly important. This entire course is a 3 combination punch. Watch the lectures, read the notes, do the homework, and then take the quizzes. Each one takes you to a higher level of understanding. Okay, I think we'll stop here.